Hi, I'm Dr. Romeo Bruni. I was an emerge doc for 30 years, and acid base is critical in the emergency room. And no, it's not hard. It's actually very easy. Even mixed disorders are very easy. You just need a clear, precise approach, systematic approach, and you won't miss anything. So let's start from the beginning and keep it simple and basic. First of all, some definitions. The final pH of the blood, which is the most important thing, can either be an acidemia, an alkalemia, or normal. That refers to the final pH of the blood. That's why it's emia. The body wants to keep the pH around 7.4 because proteins work best exactly there. Any deviance from there, proteins are going to start to malfunction. And obviously, it's also a sign of disease if you have other than a pH of 7.4. So the body will always try to keep the pH at around 7.4. So how does it do that? Well, it's got two main buffering systems, controlling the carbon dioxide and controlling the bicarbonate in the blood. This is represented by the Henderson Hasselbach equation, which is a simplification of the Henderson Hasselbach, and basically it's what you need to know, and that is that the H plus concentration, the final H plus concentration in the blood, is going to be proportional to the partial pressure of carbon dioxide in the blood over the concentration of bicarbonate in the blood. The partial pressure of carbon dioxide in the blood is controlled by the respiratory system. It's a second-to-second, minute-to-minute control where the body increases or decreases respiration depending on its needs. So if your body breathes heavier, it's going to blow off carbon dioxide, which according to this equation is going to lower the H plus. And if it stops breathing as much, the CO2 will go up, and therefore the H plus will go up. Bicarb has a similar effect. An increase in the bicarb will lower the pH, or I should say, increase the pH, because of course, as you know, pH and H plus concentration are inversely proportional. The pH is actually the negative inverse log of the H plus, but don't worry about that. Just know that a higher pH, 7.5, 7.6, is actually representing a lower H plus, and low pHs represent high H pluses. That's just the way the system works. So in this system, this is your most important equation and something you'll always follow, where the final acidity or alkalemia of the blood is going to be determined basically by the PCO2 over the bicarb. So anything that's obviously affecting the PCO2 is a respiratory problem. If something is pushing the PCO2 up, it's going to push the H plus up, so that's called a respiratory acidosis. Anything that pushes the PCO2 down is a respiratory alkalosis. On the metabolic side, of course, the bicarb is controlled by the kidney. It's an hour-to-hour correction of a buffering system. But anything that affects the bicarb is called a metabolic process. So we're talking about a metabolic alkalosis versus acidosis. Now, you'll note that I'm not using the term demia here or emia, it's osis. So for example, a metabolic acidosis, when the prefix, or when the suffix, I guess, is osis. Osis refers to a process in the body. Something's going on in the body. So when you discover by your analysis that there's a metabolic acidosis going on, then you've discovered that there's something going on. You have to go back to the patient and figure out what is that process that's going on. So it's just a clue. So where do you start? Well, paradoxically, you don't start with the blood gases. When you order blood gases, you get an oxygen, which is obviously important, but is not relevant to an acid-base discussion. You get your PCO2 and you get your bicarb. So you get those two important elements. But the critical point that you must always start is we have to introduce a new concept, and that's the anion gap. The Now the anion gap is determined from electrolytes. You order electrolytes, and in the electrolytes, you get back a sodium, a chloride, and a bicarb. You determine your anion gap very simply by taking the sodium and subtracting the chloride and the bicarb. So in a normal blood, sodium is 140, chloride is approximately 105, bicarb is approximately 25. So you have 140 minus 130, you have 10. So anion gap of 10. An anion gap of 10 is normal. That is your normal anion gap. That's what you would expect to find in blood if you test it. Important that when you're doing acid-base analysis, you must always start with the anion gap, because if you don't start with the anion gap, you're going to get confused down the road. And the reason for that is that the presence of an increased anion gap is sine qua non evidence of what we call an anion gap metabolic acidosis. If there is an increase in the anion gap, it will only be there for a reason. And in emergency medicine, they're often very important reasons. So you must diagnose if there's an anion gap metabolic acidosis. Plus, it's your starting point to then start to analyze all your other parameters to determine if there's a mixed disorder. So you always start by analyzing your anion gap. And this is the most important thing to keep in mind. And I'll slip it down here. I hope you can see this. We'll slip it in here. In a simple anion gap type metabolic acidosis, the increase in the anion gap is going to equal the decrease in the bicarb, and then we'll get it to this point soon, which will also equal the decrease in the PCO2. And why we get that, I'll explain shortly. But for this point, we got to remember this important equation, that in a simple anion gap metabolic acidosis, the increased anion gap, the increase in the anion gap is going to equal the decrease in the bicarb. Not the actual anion gap, the increase in the anion gap will equal the decrease in the bicarb. So let's work through a couple of examples so that you can see how this works. And then I'll explain the importance of it also briefly. Let's look at this example. The sodium, you get the electrolytes back, and your sodium is 140, your bicarb is your chloride is 105, and the bicarb is 15. So you look at that and you calculate your anion gap. 140 minus 105 and 15 is 120. So you have an anion gap of 10. Anion gap the anion gap is 20, which is an increase in the anion gap of 10. So in other words, your anion gap is 10 too many than it should be. Something's going on, something's accumulating anions in the blood. That is, only one thing can do that, and that's some process, i.e., that's evidence of an anion gap metabolic acidosis, period. If you have an increase in the anion gap and it's significant, anion gap metabolic acidosis, period. So you can put that down as your first diagnosis. Now, in this case, if the increase in the anion gap, which is 10, is equal to the decrease in the bicarb, which has gone from 25 to 15, which it has, you would say this is a simple simple anion gap metabolic acidosis. And the PCO2. In this patient, the normal PCO2, I forgot to mention, is 40. Now what happens is if there's some process in the body creating acidosis or eventually creating an acidemia, the brain will respond by hyperventilating to try to blow off some carbon dioxide to try to put the pH back to normal. So the normal drop in the PCO2 would be the increase in the anion gap. So you'd expect the PCO2 to drop from 40 to 30 because it's compensating for the acidosis. So a PCO2 of 30 in this case you could put it up here, the PCO2 is 30, you would say this patient has a simple anion gap metabolic acidosis with appropriate respiratory compensation, because the patient has appropriately dropped their PCO2 from 40 to 30, which they should do in a simple anion gap metabolic acidosis. Now, let's say this particular patient, their PCO2 was 20. And from our equation, we should say, wait a sec, they should only drop down to 10, and yet they've dropped all the way down to 20. There's something else going on that's dropping it more than you would expect. So in this patient, you would say this patient has a simple anion gap metabolic acidosis and a respiratory alkalosis in this point, because the PCO2 is lower than you would expect. So there's some process in the body also abnormally driving the PCO2 lower than it should be. In the same patient, if the PCO2 was 40, which normally is a normal PCO2, but we would expect in this patient, because they have an acidemia for the for the PCO2 to drop, to compensate, but it hasn't dropped. If it hasn't dropped, that means you've diagnosed in this case a respiratory acidosis, because the patient should be hyperventilating their PCO2 down and they're not. So there's some process in the patient such that the PCO2 is higher. So in that case, you would diagnose anion gap metabolic acidosis and a respiratory acidosis. So you're diagnosing more than one process. So you can see how you can start to build up and diagnose the mixed disorders. Let's look at this one down here. Here the sodium is 140, the chloride is 95, and the bicarb is 25. Well, looks all kind of normal, doesn't it? But if you do the calculations, the anion gap is actually 20 in this patient, 140 minus 95 and 20. So the anion gap is increased, yet, so right away you have that diagnosis, anion gap metabolic acidosis, yet the bicarb is normal. Well, what's going on? Well, there's obviously another process in the body lifting the bicarb higher than it should be, because the bicarb should have dropped by the amount that the anion gap went up, but it didn't. That indicates that there's another process in the body driving the bicarb up. So in this patient, you would diagnose an anion gap metabolic acidosis based simply on the fact that there's an increase in the anion gap, and a metabolic alkalosis, so pushing the bicarb higher. Let's look at this case. In here, the anion gap again is 20. So we've diagnosed, again, because it should be 10, and in this case it's 20, therefore there's a metabolic acidosis, an anion gap metabolic acidosis, period. And we would expect the bicarb to drop 10 because the anion gap has gone up 10. Yet, the bicarb has dropped from a normal 25 to 5. It's dropped 20 when it should have dropped only 10. So that tells you that there's something going on in the body driving the bicarb down more than just an anion gap metabolic acidosis, i.e. this patient also has a non-anion gap metabolic acidosis. So you've diagnosed mixed disorder. So then, based on your bicarb, your final bicarb, the PCO2 will change. So in this case, with the bicarb having gone down from 25 to 20, a drop of 20, the PCO2 should be down 20 in this patient to try to compensate. So normal PCO2 for this patient with a bicarb of 5 should be 20. And if the PCO2 is higher than that, then they also have a respiratory acidosis. And if it's lower than that, then they also have a respiratory alkalosis. So you can see how by going first to the anion gap, comparing the change in the bicarb relative to the anion gap change, and it will tell you if there's another disorder in addition to an anion gap acidosis, either a metabolic alkalosis or metabolic acidosis. And then finally, you can also check the PCO2 and see if it's appropriate, and if it's not, you're going to be diagnosing another process. So it's highly possible in any one patient, you could say that this patient has an anion gap metabolic acidosis, metabolic alkalosis, and either a respiratory acidosis or alkalosis. In other words, you can diagnose up to 3 simultaneous conditions in the body going on based just on the simple numbers, and it's not complicated, as you can see. The most important of all of these in emergency medicine, of course, is the anion gap metabolic acidosis. And that is because it's relatively common, quite serious, and many acute toxins can cause it, so you need to diagnose it quickly in the emergency room so you can take appropriate remediative action. So for an anion gap metabolic acidosis, the primary causes of that are ketoacidosis, diabetic ketoacidosis, alcoholic ketoacidosis, starvation ketoacidosis, lactic acidosis. Lactic acidosis could be various types. It can be from not having enough oxygen. There's also types that aren't related to hypoxemia. Uremia is essentially renal failure. And most important is toxins. Some of the important toxins: methanol, ethylene glycol, propylene glycol, aspirin, Tylenol, iron, cyanide. Note that for most of these, you can actually get levels, perhaps not for cyanide, but iron, Tylenol, aspirin, all of these are very important that you can get levels for. And not only that, but they have very specific and important treatments that need to be initiated rapidly in order to improve the patient's status. That's why it's absolutely essential that you diagnose anion gap metabolic acidosis as an emerge. So even though the Henderson Hasselbach equation here is the definitive equation to not only categorize but understand acid-base disorders, paradoxically, your first step when trying to sort out acid-base disorders is first to go to the electrolytes and calculate your anion gap. Is there an anion gap? If there is an increase, then you've diagnosed anion gap metabolic acidosis, period, irregardless of whether you have any final change in the bicarb, like in this case, or in fact you could have another process going on to neutralize your anion gap metabolic acidosis and have a normal pH. So it's possible for a patient with a normal pH, if you do the analysis, to uncover evidence of multiple disorders going on in the patient despite having a normal final pH. So essential stuff. Remember your Henderson Hasselbach. Always start with your anion gap, and then remember this very important equation. The increase in the anion gap should equal the decrease in the bicarb, which will equal the decrease in the PCO2 in your typical anion gap metabolic acidosis. I hope this helps. I'm Romeo Bruni. Have a great day.